that's just the condition that we've got. Okay, so now that we've imposed that, we can take our inverse Laplace transform. So h of t semicolon n is equal to the inverse Laplace transform of the quantity. Remember, anything that doesn't involve s is essentially, well, is a constant in the eyes of the Laplace inverse transform that we're taking. And so we can just bring it out the front, which is what we've got here. The Laplace my apologies. The inverse Laplace transform of 1 over s to the power of 1 minus n. Remember, this is our b value. So we're going to have t to the b minus 1. Remember, so the constant remains the same out the front. T to the b minus 1, we see we have b here. Subtract 1 over gamma of b, which is what we've got here. And therefore, our b value, remember, I know I'm repeating myself over and over, is 1 minus 1 over m. So this is great. So now we've technically got our solution. And in fact, we've extended upon the solution that we had originally, because we now have it for any value of t here. The special case that we're dealing with is just when t is equal to 1, which is going to be the next step. But just so you know, in reality, it's, this is a better solution with what we've got. This works for any value of t. Well, actually, yes, it does work for any value of t. We went through that at the start. And yeah, so we can handle any case. We're not just dealing with sine of x to the power of n. But nevertheless, we are dealing with sine of x to the power of n. So we now know in order to resolve j of n, we know that it's just h of t, comma n, evaluated at t is equal to 1, which is what we had at the start. So all we're doing here is just plugging in t is equal to 1. So all of this remains unchanged, and we've got 1 to the power of something. And obviously when you're dealing with a real number, 1 to the power of anything is just 1. And so all we end up having is what we had before, which is just this constant out the front. The 1 to the power of 1 on n minus 1 has just been replaced with 1 because that's what it equals. And we've got gamma of 1 minus 1 over n. And so what I've done in this next step is just put it all into one single fraction. So we can see here we have these on the top. So on our numerator, and then on our denominator, we have this component and this component, which is what we have here. Okay, so the next step, and we don't necessarily even have to extend it further. I'm just doing it because I'm trying to clean it up. And my goal whenever I'm dealing with these sorts of integrals, or integrals of any form, is to try and get the solution to be as elementary as possible. I don't want to be drawing on non-elementary functions where I don't have to. Now, because this immediately jumped out as a special case that I know of with the gamma function, I immediately wanted to transform it and employ this special rule because it transforms a combination of gamma functions into an elementary function. So this is an instance of Euler's reflection formula, very, very famous formula, and a special case when it's applied to the gamma function, which is gamma of z times by gamma of 1 minus z is equal to pi over sine of pi z. So again, we replace two gammas with an elementary function, which is much, much better to deal with. So therefore, in our case, we've just got z is equal to n plus 1 over 2n. So gamma of 1 minus z times by z is equal to pi over sine of z times by pi, which is what we have here. Now, the condition for this to exist must be that this quantity here cannot be a negative integer. In fact, it can't be a positive integer as well, because obviously if we have a positive integer, then that means here, if this quantity here turns out to be a positive integer, then we have sine of something times by pi, which is 0. So then we would be dividing by 0, which is obviously an undefined quantity. So that is where the restriction comes from. Well, we've got it extended here to just being the negative integers, and there's a special reason for that. But in reality, we can't have positive integers either. Okay, so the condition is, with the restrictions that we currently have on n, do we have to A, further expand them, or do we have to, let me reposition that. The current restrictions that we've got is that n is a real number, and that n cannot be between negative 1 and 1. We now have a new condition that must be satisfied, that n plus 1 over 2n cannot be a negative integer or any integer for that matter. So the question becomes, is this extra new condition already satisfied with the constraint that we've got? And if not, how do we have to extend the constraints that we've got in order to satisfy the current constraint, that has to hold, plus whatever new constraint comes about? Okay, so all I've done here, very simple approach, is going, okay, let's let this quantity equal a negative integer. And if it equals a negative integer, let's solve for the values of n, or the form of n that would happen as a result of it, and whether or not it exists already, as I said, within the existing restrictions, or whether or not we have to create further restrictions. So if I have n plus 1 over 2n, which equals negative k, where k is a natural number, so this is a negative integer. If I rearrange that, that means that if n is equal to 1 over 2k plus 1, and that certainly can take that form in terms of certain integers, that means that this quantity here would turn out to be a negative integer, my apologies, and therefore it would not work. So if we have a look at this form here, we need to, as I said, I know I'm repeating myself over and over and over again, we need to determine whether or not this is already satisfied with this condition, or whether or not we need to create a new condition. So if I look at 1 over 2k plus 1, for all k as a natural number, we see here that if we sub in k is equal to 1, we have 1 over 3. If I have k is equal to 2, it's 1 over 5, 1 over, and 1 over 7, 1 over 9, 1 over 11. But most importantly, for every value of k that exists within n, and remember, we can't have it that k is we cannot have it that, gosh, I'm really stumbling over my words. My apologies. Let me just restart this minor section again. So for all of the values of k that we're dealing with here that cannot exist, when we plug it into here, we see that the value is less than 1. Now, what's important about that is that we know that the value that, or the condition that n is less than 1 is already satisfied. We already have that n cannot be between negative 1 and 1. So for all of the values of n that make this quantity a negative integer, it's already stripped away. They're not allowed because they cannot exist from the restriction that we had earlier. And similarly too, with what we have on the denominator here, this too cannot be equal to a negative integer. That is a condition on the gamma function as well. And so if we have the exact same practice of going, okay, well, let's look at the situations that create the situations that cannot occur. I 1 minus 1 over n is equal to negative k, where k is a natural number, so this is a negative integer. If we rearrange this, we have n is equal to 1 over k plus 1. And once again, if we plug in all of the different values of n that apply, this quantity is less than 1. So just as we had with this condition here, we already have the condition satisfied within the existing restrictions. So this condition that n cannot be between negative 1 and 1 captures all of the instances that aren't allowed in this further condition that we had here and with what we had here. So this is fantastic. So we don't have to expand it. N not being allowed to be between negative 1 and 1 already takes care of this extra condition that we've seen. So we don't have to apply any further restrictions on the situation, which is great. So as a condition of that, or as a result of that, we can now jump straight to our solution. So therefore, j of n, which is equal to this quantity as we got here, is equal to, so we see here, this quantity here gets replaced with pi over sine of n plus 1 over 2n times by pi, which is what we've got here. And then we just have the remaining component, gamma of 1 minus 1 on n. And so, in terms of our integral, j of n, the integral from 0 to infinity of sine of x to the power of n dx is equal to pi over 2n times by sine of n plus 1 over 2n pi times by gamma of 1 minus 1 on n, where n is a real value, but n is not allowed to be between negative 1 and 1. Now this solution here is 100% perfectly fine, and if you were to leave it there, you don't have to go any further. We can actually reposition this so it looks a little bit nicer, but in terms of our goal, or the goal that I put forward before of saying, I want this to be as elementary as possible, we can't really make it any more elementary. But we can have situations sometimes where it's like, okay, we're dividing by sign. If we can get over having to divide by sign, it's probably better. So if there's some way that I can move sign up to here somewhere, or convert it from a sine to a cos or a tan or something like that, that generally is a better approach. And similarly with the gamma function, whenever you're dealing with something that, if you have a choice between multiplying it by or dividing by, at least for me, I would prefer to be multiplying it. So again, if you just want to stop the video here, that's perfectly fine. This solution is 100% spot on, but we can just use a couple of small rules in order to make this look a little bit nicer.